Hello, welcome to STEM Q&A. Today we'll be talking about the Jacobian of cylindrical coordinates. This is a topic in multivariable calculus, or others may say calculus of several variables. And this is a concept used in integration. And the cylindrical coordinates, if you're familiar with them, is x equals to r cosine theta, y equals to r sine theta, and z equals z. So to begin, the formula of a Jacobian is partial x, y, z divided by partial r, theta, z. So old variables, new variables, and this would just equal to the determinant of all the partials. So the partial x, as we can see, with respect to r, theta, and z, and partial y with respect to r, theta, and z once again, and then partial z with respect to r, theta, and z. So to remember how to set up this Jacobian, in the rows we have the old variables. So in row 1 we have just x's, and the second row we have just y's, third row we just have z's, and then the columns are your new variables, and then we'll just go under it. So that just means the partial of an x function with respect to r. That's all it means. So to begin, we'll start taking the determinant of this Jacobian of cylindrical coordinates. So right here, I'm gonna put determinant. And then our first partial is the partial of x respect to r. So it just means that any other variable in here is a constant. So the constant would just be theta. So the partial of this x function respect to r would just be cosine theta. So if I set this up right, cosine theta. Oh, sorry if I wrote it wrong. Cosine theta. Cosine theta. And then next I have the partial of x respect to theta. So now r is a constant, and we're taking the partial of cosine theta. So as we know, a partial or a derivative of cosine is just negative sine. So this would just be negative r sine theta. And then x, partial x respect to z. There's no z variables in here, so r and theta are constants, so this is just 0. And now moving to the next row, we have we're using the y function now. So partial y respect to r, theta, and z is what we'll be calculating. So first we got respect to r, so just the partial of sine theta, which is it would just be the partial of y respect to r, so it's just cosine sine theta. My bad, sine theta. And now the partial of y respect to theta, so this is just the derivative of sine theta. So put r cosine theta. And now, last but not least, respect to z. There's no z variables in here, so r and theta are just constants, so this would just be 0. And now we're taking the partials of z respect to r, theta, and z. So first with r, there's no r variable in here, so z is a constant. The partial of that is just 0. Now theta, no theta in here, it's just 0. Now we got z, so partial z is just 1. So now here we go. So if you're familiar with taking determinants, we pick a row to be our vectors. So the easiest is just picking the top row. So we set this up right. We have our first vector. This is just like your I, your J, and your K, if that's how is most easier for you. So our I vector would just be cosine theta. And now the determinant of, after we eliminate this row and this column, we're left with this square right here. I will highlight it for you. So the determinant of this, so this is just this portion of the Jacobian over here, and we just put it in here. So this is r cosine theta 0, 0, 1 minus the next vector, which is r sine theta. The determinant, to find what will be the determinant, eliminate this row, this column, we're left with sine theta 0, 0, 1. So it's this portion right here. So I'm gonna highlight it. So now I'm gonna put it in here. So I got sine theta 0, 0, 1, and then last but not least the k vector, the last vector, which is a 0. Even though whatever is left right here is 0, I'm gonna still write it down for you guys. So we eliminate this row and this column. We're left with, I'm gonna just do it black, this section of the Jacobian right here, which is this portion, and this will go right there. And then so it's just sine theta 0 or cosine theta 0. So now we just take the determinants. So this is cosine. So the determinant of 2 by 2, you know, multiply across, subtract whatever's multiplied across. So r cosine theta times 1 minus 0. Next, negative, negative, that's a positive. R sine theta. And now take the determinant of 2 by 2. So this is just sine theta times 1, sine theta, minus 0, and then plus 0, which is 0. So now we distribute across. This is r cosine squared theta plus r sine squared theta. So if you're familiar with trigonometry, you know that cosine squared theta plus sine squared theta, which is equal to 1. Factor out an r, cosine squared theta plus sine squared theta. This inside is just equal to 1. So in reality, this is just r. So the Jacobian of cylindrical coordinates is equal to r. And when you plug this into an integral, you have your new function of r theta z multiplied by the absolute value of the Jacobian x y z over r theta z dr d theta dz. My bad, forget the comma. And then this would just be your Jacobian when solving for your integral. So that is it. Thank you for watching. Please like and subscribe. Please feel free to leave any questions in the comment section below. And thank you for your time. Thank you for watching.